Next, we have Jérémie to talk to us about compositional verification. Thank you. Yeah, you can.
Can you hear me all right? Cool. So yeah, I'm Jérémie. I work at Yale University in Zhong Shao's team, and I'm going to talk about work we did with Zhang and Yuting Wang. And the goal of our work is to figure out how to verify heterogeneous systems. So just to give you an example of the kind of thing I'm talking about. So here's a fairly simple program built out of two modules, right? One is written in assembly. It has some kind of hello world message in here. Then at some point it's going to call into this C library file that applies a ROT13 transformation to the message. Then it's going to invoke the right system call to display the message on the standard output. Now we could have a second program that also uses this ROT13 library, right? Whose goal is to decode this message, and so it's going to read some data from the standard input, apply this transformation, invoke the right system call to display the result. And so what we want to verify here is that if we compile and link these two programs in the obvious way, and we combine them together like that by feeding the output of the first to be used as the input for the second, then it will indeed display the message hello world on the standard output, right? And this is not a complicated problem in and of itself, but what's complicated here is that, so of course we have semantics for assembly languages, the C languages, we have all kinds of program logics that can help us do that. But here we're interested on how these programs are going to behave within an environment, right? And we're going to have multiple languages that are going to interact with one another, things like that. So if we wanted to verify this the traditional way, we would have to model all of these details of like how Unix processes communicate through a pipe and so on and so forth by building a new operational semantics that has everything in it, and by figuring out ways to reason about it, right? So what we would like to do instead is to have a more compositional, more convenient way to build a model of this system from existing components, right? Certified compilers, program logics, things like that. And to be able to reuse these reasoning techniques from the pieces we use to build our model of the system. So our proposal is to use semantic level refinement frameworks to do this kind of thing. Of course, what that means is that we'd be able to express a high-level specification for the behavior we want, right? So we want that command to display hello world. We'd be able to define our model in a more flexible and compositional way by reusing existing things. Here I've described, okay, if you take all of these assembly files, link them together, load them as a command, and combine the resulting processes with a pipe, right? That's the thing we want to verify. And we want to be able to do that through a refinement paradigm where we can step by step go to a more concrete version of our specification until we reach the concretely implemented system, right? So the problem is, in a heterogeneous context, things don't always work as smoothly as that, right? Because if you think about it, you're going to have C program, assembly programs involved in this thing, higher level views of Unix processes, and so on and so forth. So things get a little bit complicated. But what we did is we used FX signatures to provide a type for our components. And we'll have components that use the operations in a signature E to implement the operations in a signature F. And the key ingredient of our framework is that we generalize these refinement steps to refinement squares. And the additional ingredient in refinement squares is that in addition to relating things of the same type, we're going to be able, when we have things of different types, like in this case, a C and assembly module, we're going to be able to express the abstraction relationship that makes them correspond to one another, right? So in this case, this refinement square corresponds to the compiler correctness property from CompCert, and we can express as this so-called refinement convention, the calling convention that's used by the compiler to validate this refinement. And using this kind of refinement squares, we'll be able to construct complex two-dimensional refinement proofs like this, where you'll be able to reuse properties expressed as refinements, things that you've proved yourself, like this code proof, or things like a compiler correctness theorem, a linking theorem for the assembly language, and other things that I'm going to discuss. So that's the basic idea. We build a framework where we have this notion of not only horizontal composition between the components of a program, but also vertical composition of abstraction relationships and of refinement squares. I'll talk a little bit, if I have time, about spatial composition, which is how we deal with how state is used in the different parts of the system. And we were able to mechanize this framework and incorporate CompCert-O, which is our version of a compositional version of CompCert, to be able to reuse all of these things that are associated with it. So I'm going to describe how this two-dimensional refinement framework works a little bit. Then I'll get into how we deal with state and go over a conclusion. So, sorry, let me. All right, so as I said, we are using a notion of FX signature to type our components, right? So an FX signature is just a set of operations, and for each one, a set of possible outcomes. And our strategies have these types, and what that means is that their behavior is going to be like this. Somebody is going to invoke an operation of F, and that's going to activate our strategy, which can then make a series of calls into E, and finally return an outcome for the operation that was invoked in F, right? And to give you an example, the interface of commands is very simple. They have one operation, which is run the command, and the outcome will be an exit status for the process, right? While the command executes, it can use read and write system calls, which means that in the end, we can use strategies of this type to specify what a command does or what a Unix-like process does. So as an example, our decode process, right? We can give this kind of specification for it, which says that if you run decode, it's going to read some data from the standard input. If it reads that specific message, it should write this message to the standard output. Now, given two strategies that interact over a common FX signature in the middle, of course, we can compose them in a typical sort of game semantics kind of way, right? So we can let them interact over the signature F and hide that signature to obtain a strategy that goes from E to G. And to give you an example, we can use this type of composition to describe what happens when, let's say, decode.c makes calls into row13.c, right? So we can combine the semantics of these two C components to see what happens when we run them together. Another way we can compose things is side by side. So here we don't let them interact, but we just put two strategies side by side and let them implement the sum of their operations, right? So the type of the resulting strategy will look like this. One example is if we want to sequence commands to implement this shell semicolon operator, right? The first thing we want to do is to combine them side by side like this. So we get a strategy which has two run operations that allows us to run either command as we wish. And then we can combine this with a sort of scheduler component that first runs the first command, then the second command, and returns the exit status of the second one, right? So that's how we can model the kind of shell operators like the semicolon or the pipe. So we can use this very simple elementary horizontal composition principle to build more complicated things. All right, so things now are getting interesting because we're going to talk about our refinement squares. So the magic ingredient here is this notion of refinement convention. And this refinement convention is going to tell you how the operations of E1 and E2 correspond to one another, but in a way that can embed some state and be history sensitive, right? So once you've done that, you can then specify that two strategies will have the same behavior in terms of the shape of the behaviors, but the specific operations will be translated between high-level views and low-level version, right? And all right. So if we use trivial refinement conventions, we'll recover a normal notion of refinement where E1 and E2 are the same, of course. Now, these refinement squares can compose vertically, right? So what before would be transitive refinement, where we can just combine things in this way. Now, when the refinement conventions are involved, we need to compose the refinement conventions themselves to compute what's going to be the abstraction relationship in the resulting composite refinement, right? What would be the monotonicity of, let's say, this layered composition operator in a classical framework? Now it's going to become a horizontal composition of refinement squares. And when refinement conventions are involved, you want to make sure that the two refinement squares agree on the ways in which the operations of f are realized as operations of f prime, right? So, and we have similar rules for flat composition that I'm not going to get into. So that's one of the basic two-dimensional framework. The idea is that a lot of properties, different properties, can be expressed as refinement squares, and then we can mix and match to build complex refinement proofs. And now I'm going to talk a little bit about how, in particular, that comes in when we're going to talk about state. So to deal with state, we use this spatial composition operation. And spatial composition is going to act on all of the objects in our framework, right? So for fx signatures, what I'm doing here is I'm annotating every operation and every outcome that's found in the signature E. I'm going to annotate it with a current state snapshot of type U, right? So that means in the case of, maybe you saw before, for example, I had this C at mem signature, and that means we have C calls annotated with the current state of the global C memory, right? Now, strategies, if we have a strategy that goes from E to F, and we extend these signatures with some state, we can let the strategy do its thing and just pass along the state component that we've added. And optionally, we can also add a transformation to the state that acts sort of in parallel with the strategy L, right? Similarly, we can define same kind of thing for refinement conventions and also compose refinement squares, right? So you can imagine there's a third dimension, and you can sort of flatten the two squares together. One that's about the strategy, one that's about the state transformation. Now, what are we going to do with that? So let me switch gears and think about what will it take to implement a counter. So here I have a very, very simple specification for a counter where you call inc once, it's going to return 0. The next time it's going to return 1, and so on and so forth, right? And we want to implement that with a C library that uses this variable. I mean, you understand this code. I don't need to go over it. So what you can remark here is that our specification uses an implicit notion of state, right? Whereas, of course, our C semantics are going to tell you how like the variable C is going to be modified by this code and so on and so forth. It's going to use an explicit state that's going to be concrete in terms of C value and live in a global memory state. So how are we going to bridge these two views is the question, right? So the first step is we can sort of deal with encapsulation by using this state transformation primitive, which is going to hide state component of type U by using an initial state U0. And what that means is that this counter, right, we can give a specification that uses an explicit state, natural number as explicit state, and that's just going to say, okay, if we're invoked in the state n, we're going to return n, and the new state is going to be n plus 1. And we're able to sort of encapsulate this state to recover our encapsulated specification. Likewise, if we have a relation between this abstract natural number and the concrete memory states, we're going to be able to use this kind of refinement square to show a refinement between the abstract and concrete state. And then we also have a way to deal with how this value is going to sit within the global memory, right? We adapted the notion of separation algebra to be used in the context of our refinement squares. And we were even able to formulate a frame property for the C-Lite language in the form of one of our refinement squares. So by combining all these kind of ingredients, we were able to incorporate Concerto in a framework. We defined a new language, C-Lite-P, that has like private encapsulated variables. We were able to redefine a whole theory of certified abstraction layers using these basic ingredients. And of course, model our example from the introduction. We hope to use this kind of frameworks as coarse-grained glue for reusable certified components, right? And together, I think we'll need to incorporate more program logics and things like that. Adding concurrency is also a very important goal. And it will be useful to make more explicit connections with higher category theory, which is a theory of what happens when you have these different composition operations that interact with one another and allows us to think geometrically about this kind of thing, right? So thank you for listening. I'll be happy to take questions. I want to point out, if you read our paper, that we were mistaken in our characterization of CCR, which does support some kinds of encapsulation and certified compilation. So we're going to publish an updated version of our technical report with a more detailed comparison with our own framework. Thank you. Yeah.
We thank the speaker, and we have time for a question.
Hi, Max New, University of Michigan. I have a question about category theory, which is, so I guess this is a double category, right? This refinements, almost?
Yeah, there's some technical details, but in spirit.
Okay, because what I was going to ask is, one of the most important new things you can define in a double category is when a vertical morphism can be sort of like minimally or maximally turned into a horizontal morphism.
Right. So conjoints and companions,
yes,
right?
Exactly.
So those are horizontal morphisms that can correspond to vertical morphisms in a way. So let me go back to this diagram here. Here, there are some versions of conjoints and companions that are involved in these corner squares here, right? So, for example, when we model how you take an assembly program and turn it into a command, this entry morphism here is going to tell you how the run operation is going to trigger a call to main, right? That's like the bootstrapping code that the thing uses. But then when we look at when we want to prove that our code is correct, we have to take into account this sort of correspondence. So that's a kind of situation where you have refinement squares that you have strategies that have conjoints and companions, and you can use them to do this kind of thing. Yeah.
Well, that's all the time we have. Let's thank the speaker once again.